Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 2 on the exponential.
In this lesson, we'll introduce the principal hero of our story, the exponential function, and dive deeper into its definition and the implications thereof. We'll also see how Euler's formula entwines the exponential function with our principal supporting actors, the basic trigonometric functions.
We begin this lecture, and indeed the course, with the question, what is e to the x, the exponential function? Well, of course, it's a function. Hence, we can plot the graph of this function and consider what the output, e to the x, looks like for various inputs, x. But how do we compute some of these outputs, let's say for an irrational input, like pi? How would we even make sense of exponentiating an imaginary or a complex number? Is it possible to give meaning or sense to exponentiating an operator, like the derivative, or more unusual objects that you may have seen, such as matrices? Well, we won't answer all those questions today, but let's recall a few facts about the exponential function. Certain algebraic properties are manifest and well known to us. From your prior exposure to calculus, you should have seen some differential and integral properties. E to the x is that remarkable function that is its own derivative, and thus it is its own integral up to the constant of integration. There's one other fact that we need to move forward, and that is Euler's formula that tells us something about exponentiating a complex input, namely e to the ix is cosine of x plus I times sine of x. None of these properties, however, tell us what e to the x really means. We therefore move to the definition for the purposes of this course. This is what e to the x is and means. We define e to the x as 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the fourth plus 1 over 120 times x to the fifth, and this keeps on going and going. Where do these numbers come from? What do they mean? Well, another way to write this is using factorial notation, that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. All the way down the line. One never stops. This sum keeps going forever and ever. Now recall that k factorial for a positive integer k is defined to be k times k minus 1 times k minus 2, all the way down until you get to 3 times 2 times 1. That gives the sequence of numbers that we saw at the beginning. Recall also that by convention, and for very good reasons, 0 factorial is defined to be 1. Thus, we could write our definition for e to the x using summation notation, as the sum k goes from 0 to infinity of x to the k divided by k factorial. This is a formula that you are going to want to memorize, as we will be using it throughout this course. Well, definitions may be nice, but what do we do with it? How do we deal with this statement? How do we even make sense of this infinite sum? Well, certainly for specific values of x, say x equal to 1, we could try to compute what e to the 1 would be as 1 plus 1 plus 1/2 plus 1/6 plus 1/24, etc. It seems as though this converges to the familiar decimal expansion for e that we know. In general, the principle that you should follow in trying to understand statements such as the definition of e to the x is to pretend that this is a long polynomial, a polynomial of unbounded degree. Now, polynomials are wonderful objects to work with, very simple from the point of view of differential and integral calculus. Recall that when it comes to differentiation, the derivative of x to the k is k times x to the k minus 1. Likewise, the integral of x to the k is x to the k plus 1 over k plus 1. Don't forget the arbitrary constant, and don't forget that something unusual happens when k is equal to negative 1. Both of these properties should be familiar from your previous exposure to calculus. Given these facts about polynomials, let's see what we can observe about e to the x. For example, if we tried to differentiate e to the x by using our definition, then what would we obtain? Well, thinking of e to the x as a long polynomial in x allows us to apply what we already know. For example, what is the derivative of 1? Well, that's clearly 0. The derivative of x is clearly 1. What is the derivative of 1 over 2 factorial times x squared? Well, it's 1 over 2 factorial times the derivative of x squared, which is 2x. We can continue on down the line, taking the derivative of x cubed to be 3x squared, etc., following the constants as we go. Now, a little bit of simplification tells us that the 2x divided by 2 factorial gives us simply x. The 3x squared divided by 3 factorial gives us simply x squared over 2 factorial. This pattern continues, since k divided by k factorial is 1 over quantity k minus 1 factorial. And what do we observe? We observe that we obtain the definition of e to the x by simply following what seemed to be the obvious thing to do. Will that work if we try to integrate as well? Let's see. If we try to integrate our definition of e to the x, 1 plus x squared over 2, etc., what will we get? Well, the integral of 1 gives us x. The integral of x gives us 1/2 x squared. If we have a 1 over 2 factorial times the integral of x squared, that's 1/3 x cubed. I'll let you follow this pattern all the way down the line and see that with a little bit of simplification, we wind up getting not quite e to the x. It appears as though we're missing the first term. We are missing the 1 out in front. So we've obtained e to the x minus 1. That's not quite the way I remember the integral of e to the x going. However, we have forgotten, as one often does, the arbitrary constant out in front. We can absorb that negative 1 into the arbitrary constant, and what we have obtained is, up to a constant, e to the x. That bodes well. Let's see what else we can do. Recall Euler's formula that tells us something about exponentiating I times x in terms of cosines and sines. What happens if we apply our definition of the exponential in this case? If we want to take e to the I times x, well, this is 1 plus I times x, plus 1 over 2 factorial times quantity ix squared, that is, I squared times x squared, etc., etc. There are a lot of terms here. Then it appears as though there are some simplifications that we could do. Recall that by definition, I squared, the square root of negative 1 squared, must be negative 1. Therefore, if we look at I cubed, we have to get negative I. And I to the 4th, being I squared squared, must be equal to 1. Therefore, we have a cyclic pattern in our powers of I that allows us to simplify this expression as 1 plus ix minus x squared over 2 factorial minus I x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. You can see the pluses and the minuses coming in alternating pairs, and the real versus imaginary terms alternating with each term. Now, if we were to do what we do when we work with complex numbers and collect all of the real terms into one part and all of the imaginary terms into the other, then what would we obtain? Well, the real portion of this expression is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, etc., with the signs alternating and with even powers of x. From Euler's formula, that must be the cosine of x. Likewise, the sine of x must be the imaginary portion of this expression, that is, x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc., with odd powers and alternating signs. Our conclusion from this rather simplistic manipulation is that we now have alternate expressions for certain trigonometric functions. The cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, etc. In summation notation, we could use a wonderful little trick to express this compactly as the sum, k goes from 0 to infinity, of negative 1 to the k times x to the 2k over quantity 2k factorial. That builds in the alternating signs and the even powers. Likewise, for sine of x, we can write this in a summation notation with a similar idea as the sum, k goes from 0 to infinity, of negative 1 to the k times x to the 2k plus 1 over quantity 2k plus 1 factorial. This gives us the odd powers of x. Now you may recall that the trigonometric functions have some very nice properties with respect to calculus. For example, you may remember something about the derivative of sine of x. Let's see what happens when we take our newly derived expression and differentiate it as if it were a long polynomial. The derivative of x is 1. The derivative of x cubed is 3x squared. We must divide this by 3 factorial. The derivative of x to the fifth and x to the seventh follow the familiar pattern. With a little bit of cancellation of the coefficients, what do we see? Well, we get 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, etc. This is an expression that we have very recently seen. This is our derived expression for the cosine of x. And you may recall that the derivative of sine is cosine. But without any complicated proof, we've derived this expression very simply by pretending that everything in sight is a long polynomial. You could write this out in terms of summation notation. It looks a bit complicated, but it's a wonderfully convenient and compact way to perform this derivation. I'll leave it to you to check that you can do the same thing with the derivative of cosine of x, obtaining minus sine of x.
We now have new interpretations for the exponential function, as well as for sine and cosine. Don't panic if these feel unfamiliar. Take a look at the bonus lecture to see a more concrete perspective and to hear a few words of comfort. Be sure to take a look at that before moving on to our next lesson, where we introduce a series perspective for a broader array of functions.